laser. So, how this laser is going to help to find out the waves which are going to be useful. So, today we are going to complete the whole chapter about the laser. Yeah. So, introduction. Yesterday already I have discussed about the introduction, how this laser is going to be useful and how it is helpful. Okay. Um, yeah, emission and absorption. Yes, I want to discuss today about yesterday I have already discussed about the introduction, how this is going to helpful for the particle in nature, that is wave nature, how this laser is going to help. So today we are going to discuss to the topic of emission and absorption of radiation. So yesterday I was already told how this radiation takes place. The radiation will be there in our body, will be there in all the gadgets, whatever we are using, it is there. We get rehydrated because we have electrons and electric field and magnetic field will be also there because we are also observing. We also observe the radiation. Because of too much of radiation, we get headache. And this is what we want to discuss about the particle, how this radiation helps to generate the heat. So what is emission? What is absorption? So in an atom, the negatively charged electrons, we see in an atom, we are talking about molecules. In an we are talking about the particles. In an atom, the negatively charged electrons revolve around the positively charged nucleus. Yes, we have the nucleus around that. Atoms will be there in certain specified orbits. Yes, we know that the various electrons at an atom that revolve around the nucleus can be represented in the energy level diagram. So every electron, so now we talk about radiation in the sense means we need to talk about electron. Okay, the electron, the effect of radiation is because of the electrons. So every electron occupies one of the energy levels as detailed in the energy level diagram scheme described in earlier lessons. According to Bohr's theory, the energy can be acquired by the electron in discrete quanta. The acquisition of energy results in a transition from one shell to the other. So, and then the atom is unstable state. When the electron is in its original level, at its lowest energy state, it is said to be in ground state. When once the atom is excited, the electron can go from ground level to the higher energy levels. Depending upon the occupation of the higher energy levels of electrons, those levels are designated as first excited level, second excited level, third excited level, etc. So we have electron, we have atoms, we have nucleus. Around that nucleus, we have electrons. So first, second, third, fourth, nth. So nth stage of the levels we can see. So first level will be more effective than second and third. So how the energy is being transmitted, according to that, electrons starts vibrating and re-radiating to the second, third level and fourth level. So when the outermost electron in an atom is in the lowest energy state, yes, outermost will be lowest energy state. As said earlier, the atom is said to be in the ground state. It contrasts when the electrons are in the excited state, and then the atom is supposed to be in the excited state. This is the concept where we need to understand more how the radiation takes place. So with this theory is very interesting and we need to know the concept, how this is taking place. When sufficient energy is provided to the outermost electron in an atom, it detaches itself from the parent atom and the atom is said to be ionized. The electron is an excited state, drops back to its original level by giving out the energy in the form of electromagnetic radiation. Whenever the electric field is there, perpendicular to that magnetic field will be there. So the radiation is nothing but happens with the electromagnetic radiations of frequency V, where V is equals to hv. E is being the energy which is being transmitted. and H is the Planck's constant, and B is the frequency. This phenomenon is called emission of radiation. This is emission, which is giving out. The energy is given. So we are getting the current. Is nothing but emission is happening. An atom is ground. An atom in ground state reaches the excited state by absorbing the energy from the external sources. It's called radiation absorption. This is a diagrammatically shown in figure. Here, HV, ES and ES. Here we can see. So excitation by absorption, de-excitation by emission. This is excitation by absorption. This is which is going out. De-excitation by emission. So the spontaneous and stimulated emissions of radiations. So what is the radiation? How it takes place? In an atom from the excited state, while dropping to the ground state, emits radiation spontaneously on its own. The phenomena is called the spontaneous emissions of radiation. The time required for the excited atom to emit radiation spontaneously and reach the ground state is known as the lifetime. Tau of the excited atom and is of the order of 10 to the power minus 7 seconds. So here absorption of a photon. So if we are talking about light, we need to take about the photon, leading to spontaneous emission of a photon. How it is. So when the light falls on an electron or a glass material or a crystal, which the energy is coming out as a light, is nothing but a photon. If N2 is the number of atoms in the excited state to any given instant of time, the rate at which spontaneously emitted atoms reaching their ground state will be proportional to the number of excited atoms in the system. So dN2 by dt is proportional to N2. dN2 by dt minus A21 of N2, where A21 is called the transition probability. This is also known as Einstein's coefficient. Integration of equation is N2 is equals to N0 exponential minus V by A of 2. So N0 being the number of atoms in the excited state at the instant 20 equals to 0 seems most atoms spontaneously emit radiation. The resultant light waves will not be in phase with each other. The resultant photons come out incoherently. The amplitudes and phases of the waves emitted in spontaneous emissions will not be the same. So the resultant amplitude of vibration of these waves emitted depends upon the nature of superposition that takes place in between these waves. If there is constructive interference between any two waves as shown in the figure, the resultant wave amplitudes will be maximum. Wave of amplitude A and wave of amplitude B. So how the radiation is taking place, how the amplitude we can take. Resultant wave amplitude, that is A plus B. So A plus B. So here we can see wave superposition in phase. So these two waves are said to be in phase with each other. Even though the wavelengths of the two photons is same, the destructive interference causes the reductions in amplitude of the resultant wave as shown in the figure. So first wave, second wave, and the resultant wave. So this is the first wave, and which is coming from here will be the second wave. So here we can see 1, 2, and 3. Yeah. First starts from this way, second starts from this way. So first, second, and third wave. So which is combining the both the waves is nothing but the third wave, that is resultant wave. So is it clear? First wave and second wave. So combining both, we get a resultant wave. Wave superposition out of a phase. So the incandescent lamp we use in daily life emit white light. In this lamp, so the passage of current through the tungsten filament causes the filament wire to be heated up, thereby exciting the atoms in the filament. Spontaneous emissions, they emit radiation and reach the ground state, thereby resulting in the emissions of incoherent white radiation. We know that what is incoherent white radiation. So fluorescence and coherence means we know that. So Incoherent means which is not same. Okay, coherence is nothing but we get same frequency, same wavelength, only the difference will be the phase difference. So that is what is coherence. And incoherent is nothing but which is not same. So that is what is emission of incoherent white radiation. So fluorescence and phosphorescence. So the phenomena of fluorescence must be first. The phenomena of fluorescence must be first understood before describing the operations of the laser. A fluorescent substance is one which emits light when it is exposed to radiation. The frequency of the emitted radiation is generally found to be lower than that of exposed to radiation. Visible light from a fluorescent lamp is emitted when the material is exposed to ultraviolet radiation. So the coating of the inner side of the fluorescent tube is sensitive to ultraviolet light produced when an electric discharge runs to the gas inside the tube. So the fluorescent material coated on the inner side of the tube absorbs the ultraviolet light and then re-radiates visible light. So what is re-radiation? So why I'm reading line by line? Because every line is very important to understand how this is being getting as an output, how this re-radiation is taking place. As I told you, when, for example, we have taken, I want to draw. Let's take a paint. So re-radiation is very, very important concept. So for example, I've taken dot. Excellent. So here, if I'm drawing a nucleus, outermost shell, we have inside we have atom also. Nucleus will be inside. Okay. So here I can draw. So here electrons will be placed. So electrons will be placed over here. Okay, electrons are placed over here, 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 everywhere. So, like that, if a light falls on this nucleus, so light falls on the nucleus, and which is the near electrons will start vibrating and it re-radiates and hits the another electron. So this process will continuously happen according to the light which is been falling on the nucleus, and the outermost will be having less radiation or the energy will be transmitted when compared to the near to the nucleus. So the all the electrons starts vibrating and all the electrons will be re-radiating. So this is a concept of re-radiation. Okay. So re-radiates the visible light Yeah, that is about re-radiation. How the re-radiation takes place. So now they have explained about this. The phenomena, as soon as the incident radiation is withdrawn, the emission stops immediately. If the elimination of the emission of radiation continues for sometimes even after the removal of the incident radiation, then the phenomena is called phosphorescence. It is also possible to excite a mixture of two types atoms, say A and B, by irradiation, while a suitable frequency, the incident radiation must correspond to a transition involving the ground state of the atoms of A type so that the incident photons can be absorbed to excite these atoms from their ground state to an excited state. So excitation by absorption and ground state, P will be the de-excitation by emission. If these excited atoms make collisions, collisions means which are connecting or which is colliding. Electrons to the electrons or atoms to the atoms. With atoms of B type, they can transfer energy to the later by exciting them. B type of atoms to an appropriate excited state as from the figure. The atoms of type A are left in the ground state and carry away any excess energy in the form of kinetic energy, while the atoms of B type can be de-excited by emission of radiation. This process is known as sensitized fluorescence. We are naming that phosphorescent sensitized fluorescence. So stimulated emissions. So in conventional light sources, the atoms do not emit radiation all the time as described earlier, and there will not be any coherence between the radiation emitted by various individual atoms. Each atom emit radiation independently, and their phases might be different. Yeah, we are going to find the difference. It's nothing but the phase and the speed. So the amplitude of the so atom to atom, electron to the electron definitely differs. So that is what we are calculating. That is what we are able to find out when the light is falling on the nucleus and all the electrons starts vibrating and radiating. So atom to atom, electron to the electron will be different. So what we can find is nothing but the phase difference. So this is analogous to the phenomenon of throwing a handful of stones in a water pond which is perfectly still. A series F disturbances will be produced and run. In such a case, the amplitude and phase of the water wave produced will be different at the resultant wave. So mention will be completely incoherent. The light produced by that, why they have given the example of throwing stones in the water is because if stone by stone it is we are throwing in the water frequency will be differing from one stone to the another stone. It takes time. All at a time it is also thrown. Also the speed of the energy which is being according to the stone it will be flowing. So the light produced. That's why incoherent is nothing but there is no equal frequency, will be no equal amplitude. The light produced by the traditional sources of the light resembles that of the water-based described above. This type of light sources are called incoherent light sources. Instead, if each stone is dropped systematically, one after the other, in the regular intervals, a series of waves of equal amplitudes are produced. The light sources of this type of characteristics are called coherent sources for same because in light we call it as coherent. In water, we can't say it is a coherent because it will be definitely incoherent source processing of light. In traditional and conventional light sources, a low intensity is another drawback. This is because of the non-cooperative effect produced by the superpositions of the various light waves, that is photons generated by different atoms. The efficiency of the light sources can be improved by seeing that all the atoms emit radiations of the same frequency at the same time. This is the atom in a light source should be excited to an excited level and then they are made to emit radiation in phase. So Einstein proposed that it is possible to bring the excited atoms to the ground state using radiation frequency. Let an atom be excited from the ground state E0 to the excited state E1. Then the excited atom by emitting radiation spontaneously reaches another level excited state 2. If a photon with energy differences E2 minus E0 collides with one of the atoms in the excited state E2, stimulated emission takes place and two photons are produced as in the figure, which are in phase with each other. This phenomenon is known as stimulated emissions radiation. So two photons are thus produced in turn may be collide with two or more excited atoms in the excited state. That is E2. So excited state is nothing but E1 and E2. Okay, how it is colliding, how these photons are generating. P is nothing but photon. So produce four photons which are in phase with each other. So it should be in equal. So P is nothing but photons, E0, E1, E2 are the energy levels. The, this process multiples a parallel beam of light energy out of the source. The process is thus responsible for the production of the high intensity parallel coherent light beaming laser by stimulated emissions. So which is emission is nothing but which is coming out. Absorption is nothing but which is taking inside. So when the light is falling on this electron starts vibrating, that is nothing but absorbing. Emission is nothing but the light which is coming out. So that is what we are talking about, emission and absorption. Okay, so what we are observing now, again we are observing the radiation. So it's a continuous process. So light is also coming out as a photon. The radiation is coming out. That is also absorbed by our body, our eyes, everything. So how the radiation is coming out is again an emission, which is an output. So which is the absorption is again, we are taking that radiation, we are consuming it, we are getting dehydrated, we are absorbing. Our body cells are getting activated and we get tired. So that is what is a continuous process of emission and absorption, it will be a continuous process. When a body is in equilibrium with an instant electromagnetic radiation field, there will be always a proportion of atoms in the excited state. The rate of emission of energy by the excited atoms is the as a rate at which the energy is absorbed from the radiation field by the atoms is the same rate at which the energy is absorbed from the radiation field by the atoms in the ground state. So in 1979, Einstein suggested that the excited atoms not only emit spontaneous radiation but also emit stimulated radiation. So the radiation is taking place equally, both sides. So here V12 PV and 1 dV is equals to, here we have given how this radiation is spontaneously emitting and absorbing. So V12 is a transition probability of matter going from the ground state to the excited state. So what is excited state? So when the light is falling on the ground state means which is in the innermost orbit and which is that energy is being transmitted to the excited state means which is going out. So when the light is falling on an atom, so on an electron, so what happens at electron also, any electron that might be any crystal we can take. That crystal also have their atomic structure. So the atomic structure on the, for example, if you are taking lithium, lithium has some outermost shell. So each outermost shell will be excited to the uh, all the electrons which are there in the lithium, niobium or oxygen, whatever the crystal we are taking, all gets vibrated and radiated and the energy will be transmitted out. So that is the beauty of the um, understanding of the inner depth of the physics. So how these electrons have started vibrating, each of the electron is vibrated, each of the electron, how it is being transferring from one level to the another level, how this energy is being. It's a continuous process. So here transition probability of an excited atom to emit spontaneously and reach its ground state. Reach its ground state. So transition probability of an atom to emit radiation by stimulated emissions and come back to its ground state density. So rho is nothing but density of ice. Density because when the light falls when the light falls on a material, we need to see the intensity and the density of the radiation. So according to that radiation, when it starts vibrating and re-radiating, that is what is output coming out as a light or a laser or a energy which is being transmitted out. That is what is the density and the intensity. How much of the intensity of the light is falling on the crystal, that much density of the energy will be transmitted as an output. So N1 and N2 are the number of atoms in ground state and in the excited state respectively. So here A21, B12, and B21 are known as Einstein coefficients. Because why we need to find the coefficients? Because of each and every electron has their own individual atomic structure. So according to that atomic structure, we can write the coefficients or we can write the coordinates. It is found in the visible part of the spectrum. So through the spectrum, we are able to find the number of atoms returning to the ground state in a given period as a result of the stimulation is insignificant of the total number of atoms returning to the ground state by spontaneous emission. At longer wavelength, the proportions of the stimulated emissions increases. The rate of spontaneous to stimulated emissions are the same for the wavelength of 60 mu. So the Einstein coefficients, let us consider the relation between the absorption, spontaneous and stimulated emissions of the radiation constants. These constants are known as Einstein coefficients. Yes, we are now talking about coefficients, how these coefficients takes place. Let us consider two states of energies are in the ground state, that is G of S, and the other in the Einstein state, that is E of S. G of S is ground state, E of S is the excited state. So let an energy of radiation of frequency V is absorbed by the ground state. The probable rate of transition of G of S to E of S proportional to the energy density, that is P of O. That is nothing but density of frequency. So P of 2 of 1 is going to be of 2 of 1, P of V, where V of 1 of 2 is a constant of proportionality and is known as Einstein coefficients of the absorption of the radiation. So the probability of the spontaneous emissions from excited state to the ground state is P21 is equals to P of 21, where spontaneous is nothing but A21 and is Einstein's coefficients of the spontaneous emissions of the radiation. So the probability of the stimulated emissions from excited state to the ground state depends on the energy density and incident radiation and is written as. So here we are calculating through this absorption of the radiations. We can write this where B21 is equal to B21 P of V, where stimulated B21 is another probability constant known as Einstein constant for the stimulated emissions of the radiation. So excited state to the ground state to the excited state. So we are going to find both the sides, vice versa. So these are the equations for the emission and absorptions should be equal at equilibrium. Equilibrium is nothing but which is flowing equally in all the directions from top to bottom. Equally it will be flowing. So that is the equilibrium of the rate of absorption and emission should be equal. So here that's why N1 of P12 is equal to N2 of P21. So N1 P1 of 2 rho of V is equal to N2 of A21 plus B of 1 of P of V. So here we get P of V is equal to N2 of A21 by N1 B1 of 2 is equal to N2 B21. Dividing both numerators and denominators with N2 B21, we get this. According to Boltzmann's distribution law, at thermal equilibrium at temperature T, so N1 and N2 we got it. So here substituting for N1 and N2 equations, we are getting a output from equation 10. We see that B12 is equals to B21. So and A21 by B21 rho of V3. So that is the ratio of the spontaneous and stimulation emissions is proportional to V of 3. Also, as a probability of stimulated emissions is the same as the absorption. So, how the absorption takes place, how the emissions takes place, how the stimulated electrons are going to be calculated, how this radiation is taking place, that's what is a calculation is given by through the spectroscopy. So, this is being observed through the step by step and they are able to calculate. So, they want to calculate each electron, how does each electron starts vibrating and radiating. So n number of electrons, if we take one crystal of any structure, the crystal, in that crystal, all the electrons have their individual atomic structure. So individual electrons in that individual electrons also starts vibrating and radiating. So in each of the electron, they are able to calculate. So they can calculate for each one of the electrons. They can calculate for the n number of electrons. That is the process of how the calculation takes place, how the energy can be absorbed and how the energy can be emitted. So this the simulation process is helping to calculate all this to find out. So the rate of absorption of energy depends upon the number of atoms present in the ground state and the rate of emission depends on the number of the atoms present in the excited state. If the proportion of the atoms, no, 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 the rate of absorption will be less than the rate of emission. So the rate of absorption will be more than the rate of emission. So for stimulated emissions to take place, the population of atoms is excited. Absorption will be more than emission. Excited state should be more compared to the ground state, and moreover they should stay for considerably longer interval of time in the excited state. Population inversions in the name given in the conditions in which there are more number of atoms in the excited state than in the ground state as shown in the figure. So here we can see the samples in equilibrium, population inversion, sample in equilibrium with surrounding radiation speed, an electromagnetic wave passing through the sample in which there is a population inversion gets amplified. So here they are calling these electrons as an population. So by example, if more energy for these electrons, all the electrons are started vibrating and re-radiating. So when the energy is falling, these photons, see the photons, the energy which is being amplified and being transmitted, how the energy is being transmitted. So population inversion and amplification, they have given a structure to explain how this emission and absorption is taking place. When the light falls on a material, how these electrons are starting vibrating and radiating and how it is being transferred as a photon. So the process in which the population inversion is achieved is called pumping, depending upon the nature of the active medium in a laser, UV, semiconducting materials, gases, chemicals, etc. Different types of pumping methods are broadly, that is optical pumping, electrical pumping, and chemical pumping, etc. In a laser of the light amplification to take place, the basic requirements, that is population inversion, stimulated emissions along the directions of the laser beam, and amplification. So here we have the HENE laser design, that is Ali Jawan and his co-workers consist of a quartz tube filled with the neon gas and pressure of 0.1 mm Hg and helium. Helium at pressure of 1 mm Hg in the ratio. The length of the quartz tube is 80 centimeters. Here they have done the experiment of the laser. So, this laser is now is in advance where it can be continuously the laser treatments are happening to the through with the biomedical instrumentation. So how this laser is keep on helping to calibrate. Two highly reflecting mirrors parallel to each other. This is the construction and working of the HENE laser. How this is being the HENE gas laser. So here reflecting plate angle adjusted. So reflecting end plates, how this laser is helping to get an as an output. So this is about the mirrors are made up of 15 to 17 layers of dielectric films of high reflective. So the reflective should be more the order of 99.998%. The two reflecting mirrors serve as cavity. So we need to know this cavity. So the lasing action and amplifications are achieved because of these reflecting mirrors. At the end of the quartz, turbo-optically plane windows are arranged making Prebuster's angle with the axis of the cavity. So we call this as an cavity to find out how this cavity is helping to excite the atoms and how this can be turned as a laser. So this laser is helping to cut and erase the unwanted things. So atoms and its gets excited. The transition of responsible for the emission of infrared radiation with the HENE laser, which is a very famous HENE laser. So the energy levels of helium, HENE is nothing but helium neon laser. HENE. So that's why it is called HENE neon HENE laser. Nothing but helium and neon laser operating in the infrared part of the spectrum. So output as coming, which is as a laser, is nothing but a spectrum. When the excited helium atoms collide with neon atoms, the neon atoms get excited to the 2s states. As I told you, we can take any crystal, we can take helium neon. So with the helium which is colliding with neon, so how that is getting excited, how these atoms are combined and how this atom falls from one place to the another place in the infrared radiation. So they have taken they are doing with the helium neon experiment, but they might have taken with this so many different crystal structures. So ultimately, this is the one which is successful. So that's why we are studying as an experimental to find out the laser. So helium and neon is the best laser, which is very popular. Here we can find the okay. Here we can find the radiations of the wavelengths ranging from 10,600 to 15,000 angstroms. We call it as angstrom because the intensity of the radiation, angstroms, why we can take it as angstroms because the intensity. So the intensity of the radiations of the wavelength, that is 115 angstrom is where is of most intense. The neon atom falls from 2p state to the first state as described earlier. By spontaneous emission, the pink color glow of the laser tube is because of this reason only. So it is also possible to excite the helium atoms to an excited state of energy that is 20.7 eV. The state is also in the state. Helium atom exciting in the state will collide with the neon atoms in the ground state and will transfer their energy to the neon atoms. In turn, these neon atoms will go to 3s excited state as well as the figure. So here we can see how this excited state takes place from helium to neon. So the energy levels of the helium neon laser operation in the visible point of the spectrum. Through spectrum, we are able to calculate. So when the atoms come to be state, the resulting radiation is required. So here we can find the intensity of the wavelength that is 62 angstrom. Generally, helium neon laser of output. Yeah, coming to the helium neon laser with an output power of 100 megawatts have been constructed. So this laser helps to find the wavelength output power also. So according to the wavelength, the outputs of the power. So applications of the laser. What are the applications? So the laser has such remarkable properties which have provided a number of applications in various fields of field science, medicine, biology, range finding, and detection, communication, weaponry, and micro welding, etc. Sorry, micro welding, etc. So medical applications, where these medical applications are going to be useful. Lasers have been successfully used in the treatments of detach, retain, and show great promise in the treatment of cancer. Surgeons are seeing the possibility of using the lasers as an important tool for microsurgery. Experiments are now underway to use laser to affect the chromosomal changes. Why this laser is so helpful? Because the cancer cells are going to be killed. So through this lasers. So military applications, where these military applications are useful. So it is used in military due to its great quantity of energy that can be concentrated. Laser has been prominently mentioned as a potential death rate in weapons of such. So it is used in military applications, scientific applications. Laser has been used to repeat one of the most important scientific experiments, Michael's and Lonnie experiment, which showed the velocity of light was constant and thus paved the way of Einstein's theory of relativity. The laser beam is employed for three-dimensional photography called holography. So laser Raman spectroscopy is also helpful. The potential field for relating the structure of the matter. So this is a summary and explanation. So coming to the last topic, that is holography. So let us see the introduction and let's find out. So the holography is a technique by which images are produced in a three-dimensional form. The images, so holography, we are able to find the each electron, how this dimensional takes place, structure the object in themselves. This method was originally introduced by Dennis Gabor in the year 1947. We know that the ordinary photograph gives us only a two-dimensional image of photo. So we have 2D image, 3D image. So this is what is photography helps to find out the 2D and 3D. In those days, we have two-dimensional images. So the focusing takes place. Now we are studying in advance, that is 3D. So this focusing takes place only in the single plane and all the other planes are out of focus. We record only the intensity distribution prevailing at the plane of the photograph while the light from the object is focused on it. The photographic plate thus records only the intensity variation, but the phase distribution prevailing at the plane of the photographic plate is completely lost. So here, Gabor suggested a way in which we can record both the amplitude of the light wave and the phase as well. This can be achieved by combining the two phenomena of interference and diffraction. So as I told you about the explanations of the interference and diffraction, we have discussed very clearly about how the diffraction takes place, how this diffraction can be calculated, how the interference takes place. So interference pattern produced by two or more coherent beams. We know what is coherent beam also. The light can be recorded on a light sensitive medium and is called a hologram. So in a hologram, intensity and the phase of the light wave will be recorded. Hence, we can get the three-dimensional pictures. We can have different perspectives of images when viewed in a different angles. As perfect coherent beam of the light is essential to get a perfect hologram, with the discovery of the laser production of hologram has become possible. Holography was received and fully developed by Leith and Thames. So preparation of hologram and reproduction of the image. So the images, hologram is nothing but the preparation of the images, how this can be done. This is the coordinates, how we are going to find the photographic plate. Preparation of hologram. The output from a laser is first separated in two different beams. The first beam consists of a ray number, that is I, and I is spent one out of by means of lens as a third mirror. The light reflected by the curved surface in the direction of the photographic plate PV. So the second beam of the laser will be numbered as I1, 1, I1 falls from the three-dimensional object. So this beam is helping 0, is called object beam 0. So as the two beams are derived from the same laser and hence are highly coherent from a specific interference pattern. So here we can find the incident beam and falling on a curved mirror, and again it is falling on a photographic plate which is again transmitted as an object. So it's a continuous process how the preparing of a hologram, how this exposed and developed photographic plate will be like a diffracting grating. We know what is grating, which is being filtered and we are getting as a proper clear output, as well as polarization is also the same, which we get a when compared to the unpolarized to the polarized light will be equal to the wavelengths, that is lambda of the incident light. So reproduction of the image, how the reproduction takes place of the photography. No lens will be used. This can be obtained by just placing a photographic plate at the position where the real image is formed. So the reproduction of the images from a hologram. So applications of a hologram. Holographic interferometry, holography microscopy, acoustic holography, other applications. It's about the complete information about the holography. The holography is a technique by which images are produced in three-dimensional form. The images are as true as object themselves. This method was originally introduced by Dennis Gabor in the year 1947. So this is a way in which we can record both amplitude of light wave and a phase as well. A perfect coherent beam of the light is sufficient to get a perfect hologram. Laser will be used as a coherent beam. So the principle of holography has many applications, different fields like holographic interferometry, holographic microscopy, acoustic. Uh, acoustic, acoustic holography is also very important because it is nothing but a sound waves. How the sound waves can be used, how this place of the sound waves are going to be ultrasound wave generated with the reference beams and optics. So acoustic holography is also very successful. So this is about the complete information about your optics that is done with the whole topics. So all the best, students. Prepare well and try to prepare your previous question papers. At least minimum 3 previous question papers you have to refer and you have to prepare. So you have a subunit, you have an internal choice also. Accordingly, that references you can take and you can prepare on the very best.